So say Geronimo, say Geronimo, say Geronimo, say Geronimo, say Geronimo, say Geronimo, say Geronimo.
Today we're going to discuss special functions. We're going to discuss three specific kinds of functions today. The first is a piecewise defined function. That means that it's going to be written using two or more expressions, and it'll be graphed in pieces on there. An example of that would be number 1 and number 2 on your notes. The second one is a piecewise linear function. This is also called a step function. This is a single expression, but the graph of it contains individual line segments that look something like a stair step. One of those piecewise linear functions is called a greatest integer function. This means the greatest integer less than or equal to x. For example, 3.6 plugged into a greatest integer function would round down. 3.6 is found on the number line between 3 and 4. 3 is the smaller of those two numbers, so 3.6 rounded down is just 3. Be careful because it gets a little tricky when it's negative. Negative 1.5 can be found in between negative 1 and negative 2. Since negative 2 is the smallest of those numbers, negative 1.5 would round down to negative 2. The third kind of function is the absolute value function. This absolute value function, when graphed, will always be in the shape of a V, and it always contains an algebraic expression within absolute value symbols. We'll talk more about absolute value functions when we get to 2.7. Example 1. This is an example of a piecewise defined function. To graph this, you're probably going to want to use a pencil because there's going to be a little bit of erasing happening when I graph this. Take a look at the first function. Y is equal to x minus 1, and this is true only if x is less than or equal to 3. We first graph the function. Negative 1 is my y-intercept, so I go down 1 and put a dot. My slope is at 1, so I go up 1 over 1. Then you want to lightly draw the line to connect the dots. Now we move on to the second part of that. This is true only if x is less than or equal to 3. So we need to find on the line where x is equal to 3. That's right here. So less than or equal to would indicate I need a solid dot on this line. Less than indicates that I need to be drawing where the x's are going down. Anything that's not part of that can be erased. That's the first part. The second part of this says that y is equal to negative 1. This is true only if x is greater than 3. So lightly draw your line at y is equal to negative 1. We know that y is equal to negative 1 only when x is greater than 3. So we need to find where x is 3. Now it says it's greater than, but not equal to, so we're going to use an open dot to represent this. Greater than would indicate that I'm going to move where x is getting greater than. Nothing else on that line matters, so we erase it. There are no more equations to graph, so we're finished with this problem. We need to identify the domain and the range of it. There are no more equations to graph, so we can move on to identifying the domain and range for this graph. If we follow our graph over to the left, we can see that the x's will continue on to negative infinity. So we are going to follow our graph to see if there are any places where x cannot be. We follow x all the way up to x is 3, and then it stops. Since this is a closed dot, it tells me that x can be 3. From here, we're going to see if we can pick our graph up anywhere else. We can pick the graph up here on the second equation, and it continues where x goes to positive infinity. There were no spaces where x was missing, therefore the domain of this is all real numbers. We can see from this graph that y will continue to negative infinity. So let's focus on what's on the graph. Y continues up all the way to y is equal to 2. But there are no other graphs above this one. Therefore, the range has to be y is less than or equal to 2. It can be equal to because this is a solid dot. Problem number 2. We've been given a piecewise defined function, and we need to write out what function created this graph. Since there are 2 pieces to this graph, I know that I'm going to need 2 functions. Let's start at the top. This is an example of y is equal to 1. If it were to continue all the way across, that would be the equation of this line. So y is equal to 1. There's a stipulation to this graph, however. This graph is only true when x is greater than or equal to 2, because that's where this graph starts. We know that it can be equal to because the dot is colored in. The next line. We need to locate a y-intercept, or at least 2 points, to be able to write an equation. We know that our y-intercept is at -4. We need to now locate a slope. From -4, I can count up 1, right 1, up 1, right 1. So our slope is equal to 1. We can write our equation now in the form y equals mx plus b. M is our slope, so 1x, or just x, and then plus b. Since b is negative, we can simply write it as -4. This graph also has a constraint. The graph starts at x is 2. Since it's an open dot, we can't say that x is equal to, but it continues where x is going down. Therefore, we can say x is less than 2. Number 3 is an example of a step function. One psychologist charges for counseling sessions at the rate of $85 per hour or any fraction thereof. Draw a graph that represents this situation. It might be best to start off with a table to represent this graph. We know that if I go in for 0 exactly, I'm not going to pay anything. However, if I go in for just 1 minute, I have to pay $85 because it has this stipulation, any fraction thereof. So anytime that x is greater than 0, I have to pay $85, all the way up to when x is equal to 1. So from 0 to 1, I pay $85. If I go just a little bit over 1 hour, the psychologist is going to charge me another $85. So from just above 1 all the way to where x is at 2, I'm going to then pay $170. If I go just above 2 all the way up to 3 hours, the psychologist will charge me $255. This is probably enough points for me to be able to recognize a pattern on my graph. The X's represent how many hours I have attended the psychologist. The Y's represent how much money he charges me. Since he can only charge in increments of $85, we're going to count by 85 on the Y-axis. Your first step is to locate where Y is $85. We're going to treat this line just as if it was a number line. So from 0 to 1, I pay $85. Since X is just greater than 0, it's an open dot. At 1, it is an equal to sign, so it's a closed dot. And it's an and problem, so I shade in between. The next one has an open dot at 1, but I'm charged $170. So we're going to focus on where Y is 170. At 1, I'm going to put an open dot. At 2, I'm going to put a closed dot. And it's an and problem, so I shade in between. The next step up has me at $255. That begins with an open dot at 2 and a closed dot at 3. And it's an and problem, so I shade between. There's a pattern here. It looks like a stair step. So at 3 on $340, it will be an open dot and a closed dot at 4. And we'll shade in between. And so on up the graph. You can see why this kind of function is called a step function. It appears to be a staircase of steps. To graph number 4, we are going to preview the equation that we'll look at tomorrow. In this equation, h and k tell me what my vertex is. K has to do with the y, and h has to do with the x. Our equation can be rewritten so that we can see x a little bit better by simply subtracting a 0. By subtracting a 0, we don't actually change the equation. But we can see that h is equal to 0 and k is equal to 1. Therefore, my vertex is at 0, 1. The slope of my equation is 1. So I'm going to go up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. We know this shape to be a V, so we can mirror each of those points across the middle, the vertex. Then just connect your dots.